All right, so here we have a drawing of our situation. We've got a force meter at the top, which is held in place by a stick and some tape. It's not going anywhere. And then we have a string connected to that force meter, which connects to the car. And the car's wheels are free to rotate, so there's very little friction there. Another string, another force meter, and another string, and another car. So that's our setup. So the first thing we're going to do in this video is solve for the tension in the string connected to the car that's labeled M3. Notice the masses up here on the right. So here we go. Let's go ahead and start by drawing a free body diagram of all the forces on that car. Okay. I'm going to zoom in here. Okay, this is not quite a free body diagram because it's got some other components, but you can see the force arrows. So we have the normal force pushing perpendicular to the ground against the tires. We have the gravitational force pulling straight down, and we have the tension of the string that's keeping the car from rolling down the ramp. Now we also have the y and x components of the gravitational force. Keep in mind that we have kind of, taken our standard system for direction, and we have essentially rotated it. So we're just rotating the system so that it matches the angle of the ramp, kind of like so. Okay. So now we have a component of gravity in the x direction and a component of gravity in the y direction. So we need to use this little angle right here, right, which is the same angle inside that triangle between FG and FGY. In this example, our theta value is 30 degrees. Okay. Now this car is not accelerating, right? We know from Newton's law, the sum of the forces of an object is equal to its mass times its acceleration, and we can be more specific and break that force into forces in the x direction only and acceleration in the x direction only, or we could do it in the y direction. The reason why I'm choosing x is because the tension force is in the x direction. So what we want to do is consider all the forces in the x direction, add them up. The only other force that's in the x direction is FGX. So we have the tension force going up the ramp and the FGX force going down the ramp. That's it. Now the car is not accelerating in the x direction. It's zero acceleration. So we could say the sum of the forces in the x direction is actually equal to 0. Now this symbol just means the sum of all the forces in the x direction. And again, the only forces in the direction are tension and FGX. Tension's going up the ramp, so we can say that's in the negative x direction, whereas FGX is going down the ramp, so we'll say that's in the positive direction. So let's substitute all our forces. We'll say negative T1 up the ramp, right? That's going up the ramp, plus FGX, which is going down the ramp, is equal to 0. Great, let's keep going. Negative T1 plus, well, what is FGX? It's just mg times sine of theta, 0. If we add t to both sides of the equation, we get mg sine theta equals t. And there we go. Now it's just a matter of substituting in. We do need to convert the mass to kilograms, 0.330 kilograms times 9.8 newtons per kilogram times sine of 30 degrees. 30 degrees equals T. And we get a tension value of approximately 1.61 newtons. Okay, so there is the math for the forces acting in the x direction, and that helped us get the tension in the rope. Now let's consider the force at the top of the string, I say rope, top of the string that's connected to the other force meter. So let's look all the way up here, right? We want to know what is the tension pulling on force meter A. Well, we actually have a lot of different things hanging from that string, and I've drawn all the forces on all the different objects. Notice that the force meter has gravitational force because it has mass. It has T1 pulling it down, and the other rope, T2, pulling it up. It also has the normal force. Okay. So the force meter is going to have three forces in the x direction. It's going to have T1, T2, and FGX. So again, we'll have to find the x component of gravity for the force meter. But just to check these off, T2 is in the x direction, T1 is in the x direction, FGX is in the x direction, but FN is not. Now, this is the car at the top of the ramp, right? And again, we have T2 that's in the x direction, that's this rope right here. We have the rope pulling up on it, or string pulling up on it, that's T1. And then we have the normal force, which is not in the x direction. And then again, we have the x component of gravity, the gravitational force in the car acting in the x direction. So we have three more forces in the x direction there. Now, what we can do for a free body diagram is model this kind of as an entire system, but let me show you why. Let's not model it as a system first. Let's consider every single force. I'll duplicate this, drop it down. Okay. Now I'm going to delete all the forces that are not in the x direction to kind of simplify our drawing. Okay, with no normal force. There is very little friction on the diagram. That's why that's been erased. All right, so we've got T1. I'm going to even erase FGY, and I'll just leave FGX, which is going down the ramp. So we've got FGX. Same thing here. I'm going to delete the normal force, and we'll even delete FG, but we'll make sure to leave FGX. That's kind of sloppy. Let's clean that up a little bit. So that's it's kind of hard to see at this point. All right. And then same thing down here. We've got, let's clean this up. And let's make sure we're only focused on the forces in the x direction. All right. So now if I said, so this is where we kind of broke the rope right here. We're modeling everything up until this point, right here. Now I said, okay, write an equation summing the forces in the x direction. I would have, starting from, I have T1, I have two T1s. Let's make sure we're being consistent. Let's call that T3 at the top, sorry. Okay. So notice that this says T2, and this also says T2 because it's the same string. Notice also that this says T1 and this says T1. It's the same string, right? Let's highlight that in green. It's the same string. That's why those forces are the same, because it's the same string, and the tension anywhere along the string is the same. But at the top we have T3, right? That's the string right here. So we can color code all the different strings. The green one right there. 3 different strings, three potentially different tension forces. Now, if we do the math, summing all the forces on this system, right? We're treating all these objects as a system, which means treat them all together as one object. Then we have negative T3 plus T2 plus FGX of the car. This is mass 1. Is it mass 1? car at the top is mass 3. Sorry. Mass 3 minus T2 plus T1 plus FGX of mass 2 minus T1 plus FGX of mass 1. So those are all the forces in the x direction. But look what we have here. We have positive T2, minus T2. We have plus T1, minus T1. Right, so those end up adding up to 0 if you subtract and add the same thing. So our equation actually simplifies to sum of the forces in the x direction equals negative T3 plus FGX for mass 3 plus FGX for mass 2 plus FGX for mass 1, right? And we know it's not accelerating, so we can say equals 0. And then, for each of these, we just plug in for FG times sine theta, and we can solve for T3 no problem. This should be pretty easy math from here on out to solve for T3.